Great, thank you. So I'm going to be talking about common knowledge. Um, Now, as you've heard many times, Joe, along with Yoram and Moshe and I did much research on reasoning about knowledge, and we wrote the book on reasoning about knowledge that it's come up several times, and that's the book. Um, Now, I'm going to focus on common knowledge in this talk. So an important issue in reasoning about knowledge is common knowledge. Uh, Now, what is common knowledge? Well, a fact M is common knowledge if everyone knows M, everyone knows that everyone knows M, everyone knows that everyone knows that everyone knows M, and so on. That's common knowledge. Now, the first full-fledged philosophical analysis of common knowledge, I believe, was offered by Lewis in 1969 at his monograph convention, which I want to say all my citations are a little flaky because the world seemed to disagree on a lot of them. So don't take the actual citation date serious. I think partly because things can be rephrased in many different ways. So now here's a fixed point definition of common knowledge. Now the natural definition of common knowledge is an infinitely long formula. Phi is C phi, meaning phi is common knowledge. That's equivalent to everyone knows phi. Everyone knows that everyone knows phi. Everyone knows that everyone knows that everyone knows phi, and so on. That's an infinitely long formula. Now, R-wise in 1988, by the way, this is also shaky. Yoram told me it was in his thesis in 1986. I left this here because Yoram said, don't worry about changing all these things. Again, citations are flaky. Different people cite different people for it. But anyway, Yoram or Barwise or someone gave a fixed point definition of finite size. They said common knowledge of phi is equivalent to everyone knows phi and common knowledge of phi. You can think about it and you say, yeah, sure, common knowledge does obey that. If phi is common knowledge, everyone knows it, and everyone knows it's common knowledge of phi. Now, it turns out that common knowledge is the greatest fixed point of this equation. In other words, every fixed point implies it, but there are other fixed points. For example, falsity. Take C phi to be false, and then the left-hand side is false. The right-hand side says everyone knows phi and C phi, well, C phi is false. Well, everyone knows phi and something false. Well, everyone knows false is certainly false. So another fixed point is falsity. Now, the dictionary definition of common knowledge is as follows. It's something widely or generally known. That's what the dictionary says common knowledge is. Now, this is too weak, as we will shortly see. So I'm now going to give some examples, some where common knowledge is attained and some where it is not attained. Now it's common knowledge among drivers that a red light means stop and a green light means go. But the dictionary definition would be too weak here, because if I'm driving in my car and I reach a green light and to my right I see someone driving towards a red light, that's not good enough. I have to know that he knows he'd better stop. That way I feel safe to go through my green light. So the dictionary definition wouldn't work there. We need something stronger. We need for me to know that he knows that a red light is stop and green light is go. So it's not good enough, as I said, that when your red light is stopped, that it's important that everyone knows this. Now, in our book, or actually in our paper, Common Knowledge, Now You Have It, Now You Don't, we comment on common knowledge in conversation. And here's an example we give. Say Alice and Bob just finished watching the movie Hair. And Alice asked Bob, what did you think of the movie? Well, Bob has to know that the movie refers to hair. By the way, in the paper, it wasn't hair. It was, I think, the monkey business. But I did hair so that this bullet would fit in one line, because my slide's going to get full. So Bob has to know when Alice says this, when she says the movie, she's referring to hair. Now, Alex has to know that Bob knows this, so he can give an intelligent answer. Alice has to know that Bob knows the movie is Hair. That way, she knows he can give an intelligent answer. Now, Bob has to know that Alice knows that Bob knows this. That because so that Bob knows that Alice will respond appropriately to his answer. So he has to know that Alice understands that Bob knows they're talking about the movie Hair, and so on and so on. Now, by the way, the top line of my slides don't appear on my screen. There's this garbage at the top, so I don't think it's going to be very important. Now, agreeing to disagree is the title of this slide, although that doesn't show up on my screen. But anyway, so agreeing to disagree. Now, the first word, by the way, if you see my head turn and you're looking at a picture, it's because I'm looking at my big monitor and not at my computer. But anyway, the first word agree in agreeing to disagree means having common knowledge. By the way, can you see the title of my slide? I'm just curious.
Yep, we can see.
Okay, so you guys can see it and I can't. So hopefully I remember what my top line is. It's covered over by options, just show video, blah, blah, blah. Anyway, the first word agree in agreeing to disagree means having common knowledge. But what is disagree? Disagree means you reach different decisions. Now, Yora mentioned agreeing to disagree. Alman, in 1976, introduced this notion of apparently, although as I said, don't take any of these citations too seriously. It may have been introduced earlier under a slightly different name. An example of this is that I think Yora mentioned is buyer and seller of the stock. So for example, the buyer, they agree. The buyer thinks stock's going to go up. The seller thinks it's going to go down. So they agree to disagree and conclude their sale. And each of them are happy. Now, there are theorems saying that if the parties share information, including probabilistic information, then you cannot agree to disagree. So if both the buyer and the seller of the stock each have exactly the same belief about the stock going up or going down, then they can't do the sale. And this is actually quite controversial. I don't want to go into it, but this, like many of these issues, there's a lot of talk back and forth about how meaningful this is. So what's this slide about? So now, yeah, the talk, I can't see my title, but it must say Muddy Children. And this is actually the example that Ava in her introduction said that Joe gives many, many, many times. And this is something that's been given many different ways, many different flavors of it. Instead of children with mud on their forehead, one version I saw a long time ago was people at a picnic with grease on their forehead. But I'm going to spend a lot of time on this particular example, not only because Joe loves it, but it is a paradigmatic example of distributed systems. And a version of this, according to what I found earliest, was published, I read it in 1953, but again, I would not be at all surprised if it happened actually earlier than that by someone else with a slightly different way of phrasing things. So now here's the situation. There are n children that are playing together. N is maybe 10. 10 children are playing together. And the children have been warned that there will be severe consequences if they get muddy. So therefore, at least this is what we wrote in our book. I'm not sure how much I believe this in real life. Every child would be happy to see the other children get dirty. They can't see their own forehead, but if someone else has a muddy forehead, too bad, it's that kid's problem. I'm not going to tell him or her. Now, during their play, some children, say K of them, maybe K is 3, do actually get mud on their forehead. K of the N children get mud on their forehead. Now, each child can see the mud on others, but not on their own forehead. So therefore, no child says a word, because remember, these childs are happy to see the other children get in trouble, according to what we wrote in our book. So now, along comes the father, who says, he looks at the children and says, at least one of you has mud on your forehead. Now you might think, big deal. I mean, everyone knows that. At least if K is bigger than 1, everyone can see some other child, some child with a muddy forehead. We'll talk later about what the father is adding, but this certainly is a fact known to each of the children if there's at least one child with a muddy forehead. So then the father asks the following question over and over. Do any of you know if you have mud on your forehead? So that's the game we're playing now. Now, assume the children are perceptive, intelligent, truthful, and they answer simultaneously. What happens? Well, here's what happened. Here's the claim that if there's K children with meta in their forehead, by the way, I'm going to go through this argument twice because it's a little bit subtle. So if you don't quite catch it the first time, you maybe you'll get it the second time. A little bit delicate. So I'm claiming the first K minus 1 times the father asks the question, all the children will say no. But then on the Kth time, where there's K muddy children, the children with muddy forehead will all answer yes. I know I've got mud on my forehead, and the other children who in fact have no muddy forehead will answer no. So let's see why this is true. We'll prove this by induction on K. So K equals 1. If there's only one child with a muddy forehead, then when the father says, do you know if you have mud in your forehead? That kid says, yeah, I must have mud on my forehead because I don't see anybody else with mud on their forehead. And father says, somebody has a muddy forehead, it must be me. So therefore, this one child with a muddy forehead will say, yes, I've got mud on my forehead. And of course, everyone else says no, because they don't even have mud on their forehead. So now we'll do this. Now let's say there's 2, K is 2 case. So say Alice and Bob are the 2 children that have a muddy forehead. Well, each will answer no to the first question because they each see mud on the other child's forehead. Alice sees Bob with a muddy forehead. Bob sees Alice with a muddy forehead. And for all they know, that's it. So they say, no, I don't know if I have mud on my forehead. But now, once Bob answers no to that first question, Alice, don't forget she's very smart. She says, aha, I must have mud on my forehead because if only Bob had mud on his forehead, then Bob would have answered yes to that first question. But Bob didn't answer yes. So the only thing left is that I too have mud on my forehead. So therefore, Alice answers yes to that second question, and similarly for Bob. Now, let's just say K is 3. Alice, Bob, and Charlie are the 3 children with a muddy forehead. Now, Alice then reasons as follows. Assume that she does not have a muddy forehead. That's what she's thinking. Then she's smart. She knows about this induction. She knows about the K equals 2 case. So she says, well, if there were only 2 children with mud on their forehead, we just proved, and she's smart, so she understands this, that Bob and Charlie would have answered yes to that second question. But they don't. So when they don't, she realizes, my assumption that I do not have a muddy forehead is false. So I must have a muddy forehead. So yes, I have a muddy forehead. And the argument for general K proceeds similarly. Let me just go back through that very quickly. Just as I said, it's subtle. I'm going to prove that by induction on K, if there's K children with a muddy forehead, then on the Kth question, those children will answer yes, I have a muddy forehead. And the other children, of course, answer no. So Alice and Bob are the 2 children with a muddy forehead. Each will answer no to that first question because Alice sees Bob, Bob sees Alice with a muddy forehead. But when Bob answers no to the first question, Alice says, aha, my assumption that I don't have a muddy forehead must be false, or Bob would have answered yes to that first question. So I have mud on my forehead. And then quickly K equals 3, Alice, Bob, and Charlie. Alice reasons as follows. She says, say I don't have a muddy forehead. She says, then K is 2. And she understands all this mathematics. And she says, Bob and Charlie would have answered yes to that second question, but they didn't. So my assumption is false. So I have mud on my forehead. So and the general K is the same. So now, what did the father add? What did he say? What information was gained? Well, let's M be the statement. At least one child has a muddy forehead. Now, of course, if K is greater than 1, there's more than one child with a muddy forehead. Everybody already knew that. So what was gained? If K is bigger than 1, what information did the father give? Why did he bother? So it seems the father provided no information if there's K is greater than 1, but as we now show, this is false. So assume the father does not announce him. He does not announce there's at least one child with a muddy forehead. He doesn't announce that. What happens? Well, the K equals 1 case, that muddy child will say, no, I don't think I have muddy forehead. No reason for him to believe it. Father's never announced anything about muddy foreheads. I don't see anybody else with mud. So no, I don't know that I have mud on my forehead. And of course, all the other children would say no, because they don't even have mud on their forehead. If K is 2, say Alice and Bob are muddy, then Alice can't infer anything from Bob's answering no to that first question, because she's smart. She says, of course he answered no. I mean, he doesn't know about mud on his forehead. So I've learned nothing from the fact that Bob answered no to the first question. I don't know if I had mud on my forehead. So she says no to the second question, and so on. So every child answers no to every question, no matter how many children have a muddy forehead. So what happens? What happened by the father announcing M? By the father announcing M, he makes M common knowledge. Everyone knows M. Everyone knows, and M is there's at least one child with a muddy forehead. Everyone knows M. Everyone knows that everyone knows M. Everyone knows that everyone knows that everyone knows M, and so on. Now, this comment I just made here was observed by Halpern and Moses, 1984, Lehman, 1984. Who knows who else earlier may have made that observation? But anyway, those are ones I saw in the literature. Now, the children are also using the common knowledge, if you think about it, that not only are they all perceptive, intelligent, truthful, but that's common knowledge that they're intelligent, truthful, because they're reasoning about other children's reasoning, so they are aware that these children are all telling the truth and they're all perceptive. So as a secret thing snuck in here, the children are using that other secret common knowledge about themselves. Now, common knowledge is a critical issue in reasoning in distributed systems. So I can't read my top line, but this is the coordinated attack problem. And I'm going to also devote a lot of time to this one. It's just another paradigmatic example of distributed systems that also we talk about a lot in our book and many others places this is discussed. Now, the version I'm going to give is due to Jim Gray, 1978, although it appeared much earlier, other forms. But one reason I want to mention Jim Gray is because he's a special person to me. There's a picture of me with Jim Gray and Don Chamberlain. As many of you know, Jim Gray used to be at IBM. He won the Turing Award, and he was lost at sea in 2007 and never heard from again. So he's a very special place in my heart. So I'm going to use this version of it, which is due to Jim Gray. Although, as I said, there's many previous versions using other metaphors other than generals. So here's the story on this problem, coordinated attack. So there's two divisions of an army. They're encamped on two different hilltops overlooking a valley where the enemy is. Now, it's clear that if both divisions attack simultaneously, they win. However, if only one attacks, they lose. These generals of these armies say, look, either we're both going to attack or neither of us going to attack. We got to do the same thing or else it would be a disaster. So now they had no initial plans for attack, but the commanding general of the first division wishes to coordinate a simultaneous attack for sometime the next day. Something else just appeared on my screen. I don't know what this is. Oh, well, anyway, covering up my slides slightly. So now neither general will attack unless they're sure the other general will attack with him. So now the generals can communicate only with a messenger. That's the only way they can communicate. They're on the other sides of the hill. And it normally takes this messenger 1 hour to get from one encampment to the other. However, unfortunately, it's possible the messenger gets lost or even worse, captured by the enemy. And the generals know this, that it's unreliable. It's quite possible the message they send will never get through. Now, fortunately, it so happens in this particular night, nothing goes wrong. Everything goes smoothly. Whenever the messenger goes back and forth, he always does it successfully. He's never get lost or is captured by the enemy. How long will it take the generals to coordinate an attack? You can think about it quietly, and you can see I'll now show no general can be reached, and so no agreement can be reached, so no general can decide to attack. I'll go through this also twice because it gets a bit subtle. So We'll try and follow it. If not, you'll see it the second time maybe. So suppose General A sends a message to General B saying, oh, let's attack at dawn. And the messenger delivers it an hour later, perfectly delivers it, no problem. Now, B knows A will not attack unless A knows B received the message. So B says, okay, I better send A an acknowledgement that I got his message. So he sends A an acknowledgement, I got your message. But B knows A still will not attack because B knows it's quite possible that the messenger got lost for the acknowledgement, so that A never received that acknowledgement. So B won't attack because B knows he doesn't know that B received his acknowledgement. Now A's smart, he knows all this stuff. He said, okay, I'll acknowledge the acknowledgement. I'll send an acknowledgement to Bob of acknowledgement to B, I mean, of B's acknowledgement. So I'll now show by induction on K that if only K messages have been sent during that fateful night, there will be no attack. So assume first K is 1. The General A sends his message to B, and that's the only message anyone sends. Well, A certainly is not going to attack because A does not know if B received A's message, so A will not attack. And of course, B will not attack because B knows that A will not attack since A doesn't know if B received A's message. So say this is true for K, I'll show it's true for K plus 1. So after message K plus 1 has been sent, the sender, say A, a message K plus 1, may believe the other General B knows only about K messages, that he never got that K plus first message. So again, these guys are smart. We already showed there's only K, then there won't be an attack. So by deduction hypothesis, B will not attack. Therefore, since A anticipates B's actions, A will not attack. So let me just go back through that quickly. By deduction on K, I'll show if only K messages have been sent, there will be no attack. So if K is 1, just one message is sent, that's it. General A sends a message to B, and that's the only message sent the entire night. A is certainly not going to attack because he doesn't know if B received it. B won't attack, even though he received that message, because B knows A won't attack. Because B's smart, knows that A doesn't know if B receives the message. And now we'll do by deduction on K that if showed that if only K message has been sent, nobody's not going to be any attack. So after message K plus 1 has been sent, the sender, say A, may believe that from General B's point of view, there's only been K messages. He never got that other message. So, and we already showed by induction hypothesis, B will not attack if he thinks there's only K messages. So since A anticipates B's reaction, A will not attack. Okay, so what's going on here is the generals cannot reach common knowledge. Now this can be a real issue for distributed systems. I mean, they didn't reach common knowledge, let's attack at dawn. They didn't receive common knowledge of that. Now in distributed systems, this can be a real issue because similarly, it follows that common knowledge can't be obtained by messages sent and received. So in general, common knowledge is attained simultaneously. When it happens simultaneously. Everyone gets that common knowledge at the same moment. So simultaneity is an essential issue for common knowledge. Now, let's see. Oh yeah, so now I'm going to talk about, I can't see my title, but I think I'm talking about Byzantine attack, Byzantine generals. And now we'll assume they're end processes and T are faulty. These are traders. There's T traders who will say one thing to one of the other participants, a different thing, contradicting to another one, or they may not respond or whatever. There's T untrustworthy processes. Now, our goal is for all the non-faulty processes to reach an agreement. We can't expect the traders to, but we want non-faulty processes to achieve agreement. Now, a wonderful theorem, again, there's a lot of history of this, but one thing I saw in the literature is a paper by Lamport, Pease, and Shostak in 1982 that showed that this is possible if and only if T is less than n/3. If less than a third of the participants are traders, then it is possible for the good guys to reach an agreement. And I have no time to go into the details of this, but But note here, we have some other flavor of common knowledge of a non-rigid set, namely the set of non-faulty processes, that non-faulty guys reach an agreement. I can't see my title here. So I'm just going to briefly go on beyond generals, including Byzantine generals, to consider weaker notions in common knowledge. Now, for distributed systems, Halpern knows this in their famous paper, Knowledge and Common Knowledge in Distributed Systems, said the following. By the way, one reason I'm calling it famous is actually this paper won the Gödel Prize, which is the highest prize in theoretical computer science for paper. So this is a wonderful paper, and the community recognizes this as a wonderful paper. So in this 1984 paper, they considered weaker notions of common knowledge. As an example of this, rather than everyone knowing M for common knowledge of M at the same instant, everyone comes to know M within some interval of epsilon time units. And again, I don't have time to go into details of this. So common knowledge is a critical, I think this is my summary slide. Common knowledge is a critical issue in many fields, including distributed systems, philosophy, artificial intelligence, game theory, and psychology. Unfortunately, there are many situations where common knowledge cannot be obtained. So we may then reach some weaker notions than common knowledge. Okay, that's my talk. Thank you.